Hey, physics students, Mr. Heinrich here, and we're going to talk about friction today. Let's get right into the definition. So, Roman numeral one, definition. It's hard to come up with just a general definition of friction because there are two types that we're going to discuss today. But I will say this, it is a resistive force between two surfaces where motion or attempted motion is occurring. And that general definition should cover the two types we're going to talk about today. So when we're moving, a lot of times we're thinking, oh, yeah, I already know about friction. We've been doing problems, right? When something slides past another surface, there's a gripping that happens between them. It's trying to resist the motion. Yeah, that's one type of motion. But what about rolling? Rolling is another type of motion, and friction also plays a role in that. So now let's go ahead and jump into the general equation, because we can personalize this equation for either type of friction we'll discuss. And it would be friction equals mu times Fn, mu times Fn. Well, this is friction, and we know that friction is a force, and therefore its unit is the Newton. That is the derived unit. What is the fundamental unit? What is a Newton really? Its fundamental unit is the kilogram meter per second squared. Remember, that's what a Newton is all about. And this is what you already have discussed with me, the normal force, which is also a force, and any force is measured in newtons. Challenge question. Looking at this thing right here, which I call the coefficient of friction, does the coefficient of friction have a unit? Think about that, and we'll come back around to answering that question. This, as I just said, is called the coefficient of friction. Now, what to say about this? Well, I'm going to give you this long, almost run-on sentence about the coefficient of friction. It's just a number, right? So it's just a number, usually between 0.1 and 0.9. So actually, it would be better to say usually less than 1. Not always. There are some surface combinations that produce a coefficient of friction that's greater than 1, but usually you're going to see a value that's less than 1. Just a number usually less than 1 that indicates how rough or smooth a surface combination is. And when I say a surface combination, I mean two surfaces that are touching each other, right? A surface combination is, period. There we go. And just to clarify, if I had something like 0.1, right, as my coefficient of friction, this would mean a smooth combination, right? A smooth set of surfaces in contact. And you could then say, well, then 0.9 or 0.99 or even 0.8 would equal rough set of surfaces. Set of surfaces in contact. Yeah, we'll write it, sure. Surfaces in contact, boom. Okay. That's all it is. It's just a number. And I'm telling you right now that there are tables that you can look up online or in the back of your book probably that have a ton of values for this coefficient of friction for two different types of surfaces in contact. We could be talking about, how about rubber or tires, right, on asphalt? That would be a common coefficient of friction that we would be interested in knowing if we were manufacturing tires, right? How about rubber and concrete for shoes, walking on concrete? Absolutely, we would want to know that coefficient of friction. How about sandpaper in your face? Not such an important coefficient of friction, but it exists. We could find any coefficient of friction between any two surfaces in contact. Let's see if I left anything out. There's one thing that we don't have to say that I want to say: not friction. When people are first learning this, they start saying that this thing itself is friction. No, it's not. It is not friction itself. It's called the coefficient of friction. And it is a unitless number. Unitless number. Put a few exclamations there. Not friction, it's not friction. It's just this number that indicates how rough two surfaces are when they're in contact with each other. And it is unitless. Let's prove it. If I solve this equation above from u, what do I get? I get friction divided by Fn, right? I would divide Fn over, and then I would end up having a Newton. Let's look at the UA, right? UA, my unit analysis, I would have a Newton over a Newton. Hello, those would cancel out. You'd have no unit. Proof right there that it's just a number. That's all it is. Now let's get into our two types of friction, now that we have some definitional stuff out of the way. Okay. Two types. I'm going to start with the easier of the two. So let's say Roman numeral 3, two types of friction. There we go. Let's start with one, kinetic friction. Kinetic friction. I usually talk about this one second, but that's okay. Here we go. This would be friction associated with sliding. Friction associated with sliding. Right, so baseball player sliding into base. You ever watch that silly Olympic game curling? It's not silly. I'm sure it takes a lot of skill, where they push that big concrete thing that slides on the ice. Sliding, right? That would be kinetic friction. You could think of all sorts of combinations of sliding. Sometimes you get a lot of speed, you're in your socks, and then you slide on the floor, right? These would all be kinetic friction. Or how about you just pulling something along, right? You're pulling something along and you hear it scraping on the ground as you pull it along. There you go. That's the one that we're familiar with. That's why I'd like to start here. What does it look like from an equation standpoint? It's the same equation we just wrote. In fact, I'll write F equals mu Fn, but we'll put a little k here to indicate that we're talking about kinetic friction, and we need to put a k here for mu. Fn doesn't get a k. Fn, the force provided from the surface, which in this case is my arm on this candle, that's acting upward, right? And it is, in this case at least, it is, if that's Fn, it's equal to mg, or the force of gravity acting down. Now if I start to slide this, that Fn is, it doesn't, and I'm sliding it like this, I'm pushing straight on, there's no change in the Fn whether we're sliding or not, so that doesn't get a k with it, but these two definitely do. There we go, and I'll come back to talking about that a little bit more, but that's really all you need to know, is we put a k to identify that it's kinetic friction. And we want to also say this about it. It is a constant, and I'm talking about the kinetic friction here, a constant value. It is a constant value, which leads me to discuss something. I'm trying to keep these notes shorter. What are the factors that actually affect friction? So I'm going to do a quick aside here for kinetic friction. What are the factors that affect really any type of friction? So we could put this back at the front of our notes, but there's probably not room for you. So I'm going to do a quick aside here, and I will say maybe over here. Yeah, that looks good to me. Aside. Factors that affect friction. Factors that affect friction. This led me to realize we didn't talk about that, and that's very important. What are the factors that actually affect it? I'm going to propose 4, and we're going to pick 2 out of those 4. You might want to pause the video and think about this. As you let 2 things slide past each other, or you try to slide something, and maybe it's not even moving, right? What things could you change in that scenario as you try to slide something, or you actually slide something, where you could make the friction bigger or make the friction smaller? Think about it. Pause the video and I want you to think about it. Okay, we're back. What are they? Well, I'm going to propose 4 of them, and then I'm going to cross out the 2 that are wrong. Okay, because there's only 2 factors out of this list of 4 that actually affect the value or the size of friction. You might have thought, well, what if I make it a heavier object, right? What if I put a heavier object versus a lighter object and try to push? And what we're talking about is if I have a heavy object on the surface versus a light one, aren't we talking about the force acting between the 2 surfaces? A heavier object would weigh heavier on the surface, and there would be a bigger Fn as a result. So force between surfaces. That might be one of them, right? Force between the surfaces, because you have a heavy or a light object. Or forget it being heavy or light, maybe as I push, and maybe as I push it forward, I'm pushing down as well. And as I push down, I'm increasing the force between the surfaces, right? So either one of those ideas would fall underneath force between the surfaces. Number 2, maybe you thought the types of surfaces. Looks like I'm going to run out of room in my little box. No big deal. We can add to it. 3, this is one that most people don't think about. What if you slid something very quickly across the surface versus sliding it slow? So velocity of slide. And number 4, to round it out here, what's another one that might affect it? How about if I had like a 2x4, if you could imagine, and I'm looking around my room to see if I have something. Sure, I got it right here. Perfect, right? What if I slid this like this versus turning it on this side and sliding it like this? Does the surface area in contact affect the value or the size of friction? So I'll say surface area in contact. Does that affect how big or small friction is? Again, pause the video, think about it. Here we go. The 2 that do not affect it are these 2. Those 2, number 3 and 4, do not affect the size of friction, though people mistakenly think these things all the time, especially this one. They're like, well, hold on, I've been in the dirt before, and then I get in mud and my car gets stuck. I don't know if this has ever happened to you, but if you're out on a farm ever, or you're out there just tooling around in the dirt roads, what you can do is you can let a little bit of that'd be funny, a little bit of air out of your tire, and the tire flattens out a little bit more, creating more surface area on the ground. And you're like, well, I get more grip then, and I'm able to go, right? Well, actually what you're doing right there is you're reducing the pressure between the ground and the tire. You're putting more surface area on the ground, and therefore reducing the pressure between the tire and the ground, and you're allowing yourself to get up and out of the mud. So this does affect something in physics, but it doesn't affect the amount of friction. It doesn't matter if you have this situation or this situation, it's still the same amount of friction in the slide. Now this, obviously, just find something in your room, put it on the table, push down on it, and try to slide. Isn't it much harder to slide it when you're pushing down than if you just push it like that? You are definitely increasing the gripping between the 2 surfaces by doing that. So this is a check. And then obviously, based on my example before, you can have examples with 2 very grippy surfaces like tire and road. But what about hockey puck and ice? That would be a very smooth set of surfaces, and therefore you would have a much lesser friction. So types of surfaces definitely do matter. So these are my 2 factors that affect friction in general. Okay, now back to this specific type of friction, sliding friction, we also call it. There's the equation, and it is always a constant value. I don't care if that object is sliding fast. I don't care if it's sliding slow, right? It's still going to be whatever it comes out to be in the problem. Let's say it's 20 newtons, right? 20 newtons. It's going to be 20 newtons if we're going 100 miles per hour, or if we're going 80 miles per hour, or if we're going 1 mile per hour. It's still going to be 20 newtons. I hope that makes sense. And is there anything else to say about this? I will probably say, nope, I'll wait till the next one, and then I'll bring this up. All right, number 2. See how quick that was? Static friction. Static friction. Okay, the word static, what does that even mean? Well, it's that thing that happens when I get my laundry out of the dryer and it sticks to me. It's that thing that happens when I take a brush and put it through my hair. No, you're thinking about static electricity. That's something else. We're going to talk about it this year. But we're talking about the idea of static being no motion, right? And we got to be careful with this idea of no motion, because actually there is static friction in some types of motion. We'll get into that. But at first, let's just understand that we're talking about an attempt to get something moving. We're attempting to get something moving. So I'm going to say friction associated with attempted motion. Friction, and I'll just throw it in there too, and rolling. Okay, it is the force responsible for something rolling as well. All right, now I'm going to put my object on the surface. Right there it is on the surface. Now I'm not even touching it right now. It's just sitting on the surface. So all there is the force of gravity down on this object and the Fn up. Okay. So right now there is no friction. That is the point I'm making. There is no attempt at motion, and therefore there is no static friction. There's no kinetic friction. There's no friction. All right. But the second I begin to try to move this candle, right, there's a grip. So I push. Let's say I push with 1 Newton. The surface says, no, you're going to push with 1 Newton. I'm going to push back with 1 Newton. So the second I try to make motion happen, static friction shows up on the scene and says, no. And then what happens next? I say, well, I'm not okay with that. I want this candle to move across my arm so my physics students can understand static friction. And so I push with 2 Newtons, and my arm says no. What I mean is static friction says no, and it pushes back with 2 Newtons. So 1 Newton, 1 Newton, 2 Newtons, 2 Newtons, 3 Newtons, 3 Newtons. But eventually, because I am an unstoppable force, just as you are, I'm going to push with enough force that static friction finally says, okay, I can't match that force. That's just too much force for me. And now we've got sliding. And now we've got kinetic friction. So as we're attempting to move it, 1 Newton, 1 Newton, 2 Newtons, friction kicks back with 2 Newtons. We push with 3, friction kicks back with 3. Eventually, maybe, hey, it happens at 4, right? I get to 4 and static friction says, nope, can't do that anymore. And now, all of a sudden, you're moving the thing, right? And we're talking about kinetic friction because we're sliding the object. So we move from this to this. So what are we going to write about that? We should also say, based on my description just now, it's a variable force, right? And what I mean by variable is it can vary. It started off just matching what I was pushing with, but as I increased my push, it matched. I've increased, it increased. So it's a variable force responding to an applied force, right? Okay, good. Good. Variable force responding to an applied force. And we're going to get to that rolling thing in just a second, but let's first just talk about it in this context. What's my equation? Well, it would be static friction equals mu s times Fn. Very important thing here. Let's make the mention right now. Mu s is always greater than mu k. Mu s is always greater than mu k. When two surfaces are not moving, past each other, but someone is trying to, or there's some applied force that's trying to make the motion occur, this value, right, that indicates the roughness or the stickiness or the grippiness between two surfaces, right, it's actually a bigger value than once you get the thing sliding. Then all of a sudden, the combination of those two surfaces, it's not as grippy, right, technical term, grippy, as it was before. And so the value actually lessens to whatever mu k was. So we have some big differences between these two types of friction, right? But what's important to understand is for a given set of two surfaces, rubber and asphalt, the mu s between those two surfaces would be greater than the mu k if the tire started sliding on the asphalt. Okay. Always. I think there's maybe a case where they're equal. I think I've seen that once. Come on, it's hardly ever going to happen. It's almost always. All right. Now, all of that said, let's talk about that rolling thing, right? Let's talk about that rolling. Hey, what about rolling? You brought that up. Yeah, let's talk about it. Okay. So I'm going to draw a picture. And there is a molecule or a particle of the object that's round that's touching the ground, right? Now, this thing is not sliding. In the next frame, let's say it's moving that direction, right? It's going to roll, and oh gosh, it's not easy to show you in this picture. Let's do this. Yeah, this will work. I'm going to zero in on some different molecules. Let's call this one 1, 2, 3, 4, 5. We're just looking at a set of molecules or particles on the rolling disc. Well, in the next frame, what would we see? It would roll to, yep, that's right. There's one, but who's touching now? Molecules 1 on the 1 slot are not touching. Which particles on the rolling object are touching the ground? The particles that are lined up with 2, 3, 4, 5. It just rolled. Maybe we should show like this, right? It just rolled. And now these particles are touching. Is there ever any sliding going on? No, there's never sliding going on. When this thing rolls, a whole other set of particles leave the surface and a whole new set of particles engage with the surface. There is no sliding. In fact, it is gripping the entire time, which is why it can roll. It's the reason it can roll. And here's the interesting thing. No, I'll leave that alone. That's the idea between these two surfaces, that there is not sliding friction. It is a static friction that's allowing that wheel to grab and turn so that a whole another set of particles can grab and turn it, grab and turn it, grab and turn it. Okay. So we could say maybe a little verbiage here would be particles grab and rotate. Grab surface, I should have said surface here, so maybe I'll put a little caret here, surface, and rotate the object. Very important to understand there is no sliding occurring. Enough with rolling. Let's look at a graph that associates these two. So we're going to put in next on numeral 4, graph associated. I just put graph of static and kinetic friction. How about that? Graph of static and kinetic friction. Very good. All right. Let's throw it down here. And I'm going to make this my friction axis. And we're not going to say it's static or kinetic. We're just going to say friction in general. Okay. And this will be my applied force axis, also measured in newtons. So what we said before is that static friction is this variable force. So I push, let's say we have a box on the ground, right? I'm trying to push the box on the ground. I push and friction says, yeah, I'll do that. I can do that. I push a little harder, static friction grows again and says, yep, I can do that much as well. Again and again, let's just do a couple more of these. Yeah, there we go. So we're plotting the points of applied force and static friction in this case right now, right? And you'd actually get a trend, right? So as I push, static friction pushes, so on and so forth. And we finally get to this value though. Right here, static friction can no longer withstand how much we're pushing. Can no longer withstand how much we're pushing. So I'm going to say here that this value right here, max static friction, we have maxed it out, can no longer match our applied force. Right? So if I push with just a little bit more, and you've experienced this, if you're trying to push something across your room like a dresser, you're pushing and you're pushing harder, and the thing is not budging. And then there comes a moment when you get it to move and you feel this jerk happen, especially when there's a lot of resistance between those two surfaces, a lot of static friction, and you feel this jerk, and then all of a sudden you get it sliding, and it's actually a lot easier to keep it sliding, right? And that's because kinetic friction is always less. Once you're sliding it, kinetic friction, it's always less than the maximum static friction value, because this is what happens next on the graph. It dips down, there's like this jerk, right? And then all of a sudden, it's easy to keep it sliding. It doesn't matter if you're running with it or going slow with it, it's just easy to keep it sliding compared to that maximum force you were applying to get it to move in the first place. So at this point, right here, I don't need to, this is where the graph kind of, it's not wrong anymore. Like I could apply more and more and more force, but keep in mind, what did I say about kinetic friction? What did I say about kinetic friction? It's a constant value. It doesn't matter if I start pushing with a ton of force and I speed this thing up, or if I just stay at whatever force this is to just keep it moving, right? It's gonna just, the kinetic friction acting back will always be the same value. So let's put in that this is, and I'm gonna keep going back this way just so you can see this is my FK value, and this was my FS max value. Right there and right there. And I want to show you that this is agreeing with what we wrote. Kinetic friction is a constant value regardless of how much more force we apply or how little we decide to apply. That will always be the same amount. If you're still struggling with the idea, you don't have to draw what I'm drawing right now. I could push with all of this applied force, and guess what? Kinetic friction would just stay that. I could push with just that much force, right? If the thing's already sliding though, kinetic friction is still the same amount. It's like, yeah, I'm gonna stay at 20 newtons. Okay. These values, all static friction. All of this part of the graph is associated with static friction. All of this part of the graph is associated with kinetic friction. To find the values of those frictions, you have to look at the y-axis though, right? Because that's where your friction is. Let's make the statement, because I don't think I made it obvious enough in the previous part of the notes. We will say this: kinetic friction. Kinetic, too many T's in there, friction is always less than the max value of static friction. A lot of concepts here, guys, a lot of concepts. Another interesting side note is if I have to apply like 20.1 newtons to get the thing sliding, as soon as it's sliding, I can actually back off again to 20 newtons to keep it sliding. It's interesting, right? So if it's not moving 20 newtons, I'm pushing with 20 newtons, it's not moving, it's not moving. But then all of a sudden, I go 20.1 in my example, and it starts to slide. Well, now what can I do? I can back my force off to 20 newtons again, because that kinetic friction value is less than the max static value, right? So 20.1, and well, 20, static friction said, no way, 20, I can do it. 20.1, boom, we get the thing sliding, but as soon as we get it sliding, we can back off our force a little bit to keep it sliding, because that kinetic friction is always less than the max value of static friction. I hope that example didn't confuse you. We will definitely do a lot of problem solving with this stuff. Thank you so much. Talk to you soon.